I'm here to talk about substation condition-based monitoring to increase reliability. I work with Dynamic Ratings. For those of you that are not familiar with us, we've been around since about 2002. We do online monitoring for substation equipment to include power transformers, circuit breakers, switch gear. We are now getting also into some distribution monitoring, IoT devices where we're doing power quality and that sort of thing for your distribution equipment, even down to small distribution transformers. So learning objectives for this one, we're going to look at monitoring transformers. I think one of the biggest things you need to understand anytime you're approaching monitoring of any equipment, why it fails. I spent a lot of my career out in the field, and I've seen a lot of failures of different equipment, and recognizing those failure modes and the symptoms that lead up to them are a big portion of being able to determine the correct way of going about monitoring equipment. We'll talk about DGA monitoring, and with that DGA monitoring, the oil analysis, which is critical to determining the true life you have remaining of that equipment. We'll also look at bushing monitoring, as that's one of your larger failure modes. And then we're going to take a short look at circuit breakers and kind of the same thing, the failure modes that happens with that, the effects of through faults, so slow operating breakers and how that affects your other equipment in the substation, and the online monitoring solutions that we have available. By all means, this is going to be a very quick kind of overview of the different things we do in the equipment that we monitor. So questions are welcome. And if you'd like to get in touch with me and follow up afterwards, please do. So when we take a look at transformer and failures by component, and this is less than 300 kV, windings for 52% are going to be in windings, bushings around 16, and tap changers around 16. Then you have your leads and others. So majorities are associated with windings. However, as we get into this, we're going to take a closer look, because winding failure could be anything from excessive moisture ingress to through fault exposure. So this is just really kind of a broad statement to make as to why transformers fail, and hopefully we'll get a closer look and kind of really dig in on the root cause of these problems. So again, here we have through faults at 57, turn to turn short 17. So total combustible gas 10, design flaw 9. So that in design flaw, we're kind of looking at the infancy stage of transformers most of the time, lightning, other, in human error. So types of online DGA monitoring. What are you trying to accomplish? And this is something I really like to go into with my customers. Depending on this depends greatly on what kind of manual maintenance you're actually performing on your equipment. So we have to just determine, do we want to go with a single gas, or do we want to go with multi-gas on a particular unit, and understand the advantages of both these approaches. With single and composite gas monitoring, mostly based on the production of hydrogen, and that's due to hydrogen occurring through all the thermal conditions. So anytime you start to see, or in most instances, when you start to see a transformer failure, you will have a thermal condition occur inside the equipment, at which point around 150 degrees C, we'll start seeing hydrogen and methane production. As that accelerates, 250 methane turns to ethane, at 350 ethane to ethylene, and then around 500 degrees we start seeing acetylene. However, the hydrogen does not change; it produces through all that range. Therefore, that's the purpose of using that as the basis for single gas monitoring. But that being said, we cannot identify the type of fault that's occurring by hydrogen alone. So it serves as sort of a smoke detector for these faults. It's a good indicator that something's going on, but you're going to have to look into it a little further to actually determine what the actual cause of that problem is. With multi-gas, we can provide 3, 5, 7, 9 gases. I've seen this everything from an acetylene hydrogen type setup to full blown with nitrogen and oxygen values included. Now, the nice thing about multi-gas is it does allow you to go through your online monitoring and do a complete assessment of what's actually occurring with that transformer by doing some trending and looking at different ratios of gases produced. So really, this allows you to extend the amount of time that you're spending taking these manual samples every year. I've always found it a little odd. You find companies will spend a lot of money on these 9 gas monitors. And again, when you start talking about the difference between single gas and a multi-gas, with single gas, you're looking at an investment as low as $2,000 to $3,000 for just a standalone hydrogen monitor. Multi-gas, you're getting up in that $30,000 to $60,000 range. So the multi-gas, the advantage of over that is that you can sit in your office, you can pull it up and actually do an assessment on, do I have a 2T2 type fault? Did I have an arc occur in this transformer? Is it just partial discharge solely that's occurring? And also it lets you trend your carbon dioxide ratios, which gives you a good idea of level of cellulose degradation that's related to that event. This also helps a lot, which is another thing that causes cellulose degradation, is moisture ingress into transformers. This one, when you start looking at this in your DGAs, this type of failure is going to be a little different, as you generally will not have a lot of gassing to indicate that you're having your solid insulation system breakdown due to moisture. So, however, through trending of these carbon dioxide ratios, we are able to detect some of that. So what you really have to ask yourself is, do I just want a warning that I've got something going on, at which point I can go out and do the necessary DGA testing or electrical testing to determine the problem? Or is it a very high value piece of equipment, which I really can't get out of service that easily? In that case, we probably want to go with the multi-gas so we could do real-time analysis without having to de-energize that equipment. So, key gas monitoring parameters. We're talking about hydrogen monitors here, or the composite monitors, gas monitors. And what this allows us to do is really know, because of the low cost, we can spread it across a large portion of our system. So you can base these alarms, they can be based on either a total ppm value. So going by IEEE, I think around 100 is where we change from condition 1 to condition 2. Or we can base on a rate of change. I really like the rate of change approach with this. I've seen a lot of transformers that, depending on loading, the environment, the way they're being used, 100, 200 parts per million of hydrogens may be normal for that piece of equipment. And that's why I would recommend, anytime you're setting up these alarms, you really need to go back and review your historical data and see what is normal for this transformer. It does vary from piece of equipment to piece of equipment. With the rate of change value, and I'm talking a daily, weekly, monthly rate of change, I am much more concerned about a transformer that has gone up 50 parts per million in the last 24 hours than I am a transformer that's maybe sitting on 200 parts per million and has been for 2 or 3 years. This relates the same to power factor. If you're looking at bushings, some of your older bushings do tend to test high. I think when I was working with utility, actually I saw some of them that may be running at 6%, and they had been that way for years and years and years. So establishing what's normal for that equipment is imperative when we're trying to determine where to set these alarm values. Also, do we want to monitor in a headspace or a drain valve? I know most of the hydrogen monitoring to this point has been done via a drain valve mount of your hydrogen monitoring. However, if we've really been pushing the approach of monitoring gas space. So we're talking about nitrogen blanketed type transformers now, where you do have a gas space available above the oil. The reason being for this is that we have a much higher concentration of our hydrogen there, roughly 20-1 of what we would have saturated in oil. And that is highly dependent upon the equipment being, the hull being the whole integrity of the hull. So as hydrogen is generated in the oil, it quickly moves to your gas base. And if you do not have a well-sealed transformer, you don't get that, you don't really achieve that equilibrium between the headspace and the oil. Therefore, I've seen instances where, a lot of instances where you'll take DGA samples, you'll see maybe a lot of ethylene, some of your higher temperature gases produced, and very low hydrogen values. And a lot of this can be attributed to the way that oil is actually dispersing to the headspace, and is maybe due to a leak somewhere on the transformer. You're not getting that equilibrium between the headspace and the oil. Also, the hydrogen disperses much more quickly across the headspace. It's not really a homogeneous distribution of hydrogen in the oil. It takes a long time for that to occur. So if your fault is occurring on the opposite side of the transformer from where your hydrogen valve is mounted on that drain valve, it could take weeks or months before you actually pick up that event is occurring. With headspace, you tend to have almost an instantaneous dispersal of hydrogen when it gets in the headspace, allowing for a much earlier detection of hydrogen generation. And also, it's a more reliable trend than what you would see in oil. Because oil is, the hydrogen readings oil are heavily based on how the oil circulates. So if you have forced oil cooling on a transformer, of course, your dispersion will be much better. With natural convection, it's a little bit slower. So the rate of flow of oil will play heavily on how long it takes you to actually see that hydrogen generation occur at the drain valve. Whereas in headspace, it is an almost instantaneous type detection. Again, but with hydrogen, once you do receive one of these alarms, you will be required to pull a full DGA, and you will need to do some historical trending to actually determine what type of event is occurring. So when we talk about these online multi-gas and manual samples, this is just a quick run through for those of you that aren't familiar of kind of what we're looking for when we look. There's certain signatures in DGA that we look for when doing these analyses. On the top left, we're looking at arcing in oil. A good indicator of this, you'll see about 2 times the amount of hydrogen that you do compared to acetylene. That is assuming that this is not a free breathing transformer or a tap changer. If you have free breathing, your hydrogen values will always be very low. So another really good indicator is to look at your ethylene values compared to acetylene. Generally with a arc and oil, we'll see about 10 to 20% of ethylene to acetylene produced, which is a good arc indicator. With partial discharge, of course, hydrogen is going to be our major indicator of that, with some low levels of methane also being produced. When we're looking at a high thermal fault that has not yet reached that 500 degrees C point, we're going to see ethylene being the leading gas typically in that. So this would be anything from, starting to develop a short turn-to-turn short, loose connections, that type of thing, where we're going to see that conductor really starting to heat up. And then overheated cellulose, they're giving carbon monoxide as your leading gas for that. We're going to go into the ratio between carbon monoxide and carbon dioxide a bit. I feel like this can be a little bit misleading, as again, CO production is it quickly migrates to headspace and quickly gets out of any leaks you have on that transformer. So we're going to look at some incidences where actually CO values haven't changed a lot, but the ratio between the two, CO, CO2 gas, have changed. and we were starting to see the beginnings of failure of the solid installation system of that transformer. So when I was with utilities, these were actually two samples that were brought to me. The one on the left was actually one of my transformers. The one on the right was actually a neighboring utility that had a trip out and had sent this to me to kind of take a look at. And I found it interesting because obviously looking at this, we can see that, yes, we definitely had some type of arc occur in this transformer. The ethylene value being higher than acetylene is not unusual to see when you actually see in a tank arc. But between these two samples are really just not a lot of difference. And I gave it in percentages here, but also the overall part per million values were very close to being the same. And so these were the two results. Mine was obviously was a winding failure, and we ended up having to take that transformer out of service and replace it. However, the one on the right, which was my neighboring utility, was simply one of the leads had arced across to some of the support frame in the transformer. Now it was odd because they were getting ready to actually take this transformer and replace it. And I took a look at the DGA samples, and going by the carbon oxide ratios, I'm saying, no, you didn't have a failure. There didn't seem to be enough cellulose breakdown involved. So you need to investigate a little further before you actually scrap this one out. And important to mention, both these units, after they did both trip off while in service, there was a power factor test was attempted to be run on both of them, and neither one of them would test. Of course, with the lead being burned off this other one, there was never enough current built up, and the power factor set just tripped out in both cases. So it looked like failed windings in either event. So what's the big difference? When you look at my transformer on the left, the one that was the coil failure, we were running about 120 to 1 ratio of CO2 to CO. So that was pre-event, before the arc actually occurred. Post-event, that ratio had dropped down close to 2 to 1. So we had seen a large drop in the CO2 to CO ratio. If we go over to the one that was simply a lead fail, you can see that they were only 7 to 1, and it only dropped to about 5 to 1, or slightly over 5 to 1. So I did a lot of research on this, and I have several papers floating around out there if you'd like to look them up. But not just this one instance in failure, but also when doing analysis on transformers that are in service, when you have nitrogen blanketed transformers, you tend to see CO to CO ratios that actually go higher. It is typical to see this go up and constantly be moving higher during the life of that transformer. When you start seeing decreases in this ratio, it's a good indicator that you're starting to have breakdown of your solid insulation system. Or during an event like this, when you see a large drop, it's a good indicator that you had a large amount of cellulose involved with that event. Also important to mention, while there's 7 to 1, 121 levels, again, fairly close to the same in the total ppm value. So this would be another example of one of my units I had in service, and again, we were producing acetylene. If you look down here around this May, so if we start here in May of 2001, we're seeing a couple of parts of acetylene produced, quite a bit of ethylene. So not enough to indicate that we've had an arcing, but definitely that we have some type of severe overheating going on with this unit. And so this was opened and inspected several times. So you see a lot of up and down, but we did get up as high as 575 parts of ethylene at one point, which was by no means normal. If I had the history prior to this, this was actually not much of a gassing transformer up until this event started in May of 2001. We ran power factor tests. We ran SFRA tests, everything we could think of to kind of find this problem. And again, acetylene usually being the first thing everybody's eye wanders to, you start to think, well, okay, this is a transformer I'm about to lose. However, when we look at the ratio of this transformer, it's steadily moving up. Now, again, this is never going to be just a smooth linear line. You're going to see up and down. But if you were to throw a trend line across this, you'd see that it was steadily increasing. So after going in this multiple times, actually went in somewhere around, let me go back. Somewhere around this 2013, 2014, went in this unit and actually found that one of the NEMA pads on the low side had a loose connection. It had simply, and it had heated to the point that it was starting to cause some discoloration. We tightened it down. And again, this transformer is in service today. So that was 7 or 8 years ago. So again, this CO2 ratio is a really good indicator as to, is this a problem I can fix or not? As the ratios, the more the ratio is dropping is a good indication that you have a lot of cellulose involved, which is most likely going to be a winding incident. Very low amounts of drop in this ratio. And when I say large drops, I'm saying over a period of years. And usually I look for a drop of about 70%. That would be when I was really concerned. I also had several transformers where I saw these large drops in ratio, and these would be wet transformers and that type of thing, where this ratio would drop and I wouldn't have a lot of gassing present to indicate that I was having a problem. So that's why it is important, even if you are going with a key gas type monitoring, that you keep up those annual samples and do those trends, because again, with certain types of failure situations, you're not going to see any of these hot metal gases being produced. But however, when you would see that drop in that ratio of 70% or so, generally you would be within 2 to 3 years of failure of that unit. That would also be reflected in offline testing usually. So now we're on to bushing monitoring. And again, a lot of companies are doing this with offline testing. It's usually done on a cyclic type maintenance. So we're looking at about every 5 years they run these tests. Many insulation deficiencies can be diagnosed by analyzing behavior of insulation at normal and elevated temperatures. So a lot of problems with the offline method of bushing testing is a lot of times that transformer will be taken out of service a day ahead of time, which gives the transformer an opportunity to cool down. And also we are testing what may be a 161 transformer. Now we're going to test it at the 12 kV. So we're going to look at how these can have an effect on that power factor. Also, the online monitoring saves you a lot of time in your maintenance. It takes a lot of time to get a transformer out of service, get all your grounds hung, get your drops removed. So generally, you're looking at a half a day to a day just to do this offline test. And online continuous monitoring is often able to detect bushing abnormalities much earlier in their inception than traditional offline testing. I've seen a lot of instances where bushings were testing very well offline, and then customers would have them online and get their bushing monitor and say, hey, my bushing monitor is not working or is malfunctioning. And actually, no, it wasn't, but the problem had not reached a severe enough level to be detected with the offline testing yet at that point. So this is kind of goes through how those temperatures and voltage levels can affect. If you look at this blue line at the bottom, and we're testing at 10 kV at 25 degrees C, and you see it's a relatively level reading for all of these tests. So we're not really seeing any increase in power factor at all, and this would be very closely related to your offline test. If we take that 10 kV and step that temperature up to 70 degrees C, now we're starting to see a slight increase in power factor percentage. And this is starting, even as time goes on, at around the 200-hour mark, we start seeing that increase starting to accelerate. If we step up to 70 kV at 25 C to perform our test, you'll see we're getting up over 10% at times with this power factor, even though we're down below the 1% that would be recommended with our regular 10 kV at 25 C offline test. We're starting to see a lot of changes in the power factor. And then if we step up at 70 kV at 70 C, which would be very close to what we see in service, we start to see this power factor approaching 20%. So this is actually a bushing where we're starting to see it go into a failure mode. However, it hasn't even reached the point where you would be aware that you had a problem with your offline just using offline testing. So we're going to quickly talk about breaker failure as well, and how it affects our other equipment. So consequences of breaker failure: excessive through fault exposure results in mechanical distortion of core and coil assemblies. We're talking about our transformers. So as these breakers are slowing down and not operating at optimal performance, we're going to see more exposure of through faults on our transformers, which is this mechanical distortion. Also, we're going to see physical and thermal damage to the transformer cellulose insulation system. A lot of times, neither one of these will be able to be detected with your offline testing until their latter stages. I've had instances where transformers took a fault actually and tested well. Had a low side bushing failure where a transformer, actually we ran a power factor test after the failure. Power factor looked good. We had almost no change in capacitance. So because the failure was so close to the core and coil assembly, I asked for an internal inspection to be done, at which point we found that the blocking of the transformer had shifted about an inch off the line. All of the bracing had been shattered, holding our leads together. So this was not indicated at all with the power factor test. We had just seen a small change in capacitance. We actually had to run an SFRA test at that point, or I had them run one just to see what it looked like, at which point we could see the change that had occurred. So we need to limit these through faults by these slow operating breakers. And with that, we can reduce our outage time and the frequency of these outages. It reduces potential to damage to adjacent equipment. And also, with these misoperating breakers, we're compromising safety of utility personnel and the public, and you have a reduced system reliability. So when we talk about breaker failures, what are we saying when we say a breaker failed? There's actually two types of modes. So as a transformer, we kind of got to offer on with that. With breakers, we have major and minor failures. Major failures is when a breaker fails to operate. So a command is issued and breaker either does not open or close. And if we look at the percentage of that, we're going to say somewhere around 75% of that is going to be related to mechanical problems. So we're talking linkage, lubrication, those type of issues are about 75%. Now, when we get into minor problems, and I feel like this is a much bigger issue than a lot of companies realize, we're getting up near 90% range of these mechanical problems. So minor problem, we're talking about a 3-cycle breaker that's not opening for 9 cycles. So we're tripling the amount of the duration of through fault that our equipment is seeing with these breakers. And what's really scary about this is I think a lot of times utilities do not necessarily even know this is occurring. Because if you're only doing offline timing and travel tests, that first operation of the breaker often masks this problem. Once you operate a breaker once, you've kind of broken everything loose. You've got your grease mixed back up, and that next test will probably look pretty good. Sadly, in service, we do not get that warm-up operation on a fault. And so that first trip time is going to be the actual trip time. So this is kind of just a breaker failures as observed at one of the utilities in the southeast of what they're looking at. So mechanism misoperation being the largest portion of failures they had. And most of that's due to wear, misalignment, and lubrication. And you can see that was about 60%. Then, of course, with SF6 breakers, you have your low pressure. And that was a huge problem that we had, where you would constantly be topping off breakers. Also, with hydraulics and pneumatic systems, you have leaks that develop. So loss of stored energy to that. And that ends up being about 25%. And then trip circuit, it does occur at, usually there's good indicators as to why you're seeing these failures of the coils. But that's down low, under 10%. That's actually the problem causing the breaker not to fail. The good thing about this, these are all very easily monitored. And I'm sorry, I was kind of covering up the top here. I'm trying to get through this. Okay, so kind of a review on this. Increased interrupting times due to degradation of lubrication. And again, if you're only running offline tests on your equipment, you're not going to catch a lot of this. The utility I came from actually was doing only timing and travel offline for years and years and years. When I became asset manager about 4 years before I left that company, I had implemented some first trip testing, and it was amazing the amount of breakers we found that were actually slow on the first trip, that we had no idea we had problems with. Another event that can occur between these inspections, and these offline tests, again, we're looking at 5 to 8 years is how often this is getting run. So a lot can occur in that period of time. Heater failures. A lot of times this happens between inspections. When it does, I've seen control circuits where they had the actual paper fuses in them that had actually just fallen apart. So our trip circuit was broken completely, and we have a failure to operate. It's also a degradation of your wiring, and then your electrical components. Leaks in hydraulic and pneumatic mechanisms, resulting in failure to operate, and charging motor failure, which is a huge one. We had a lot of the old oil circuit breakers at my utility. There was very few stations you could ever set foot in where you did not hear at least one compressor start up every time you walked in. And the same with hydraulic. We had a lot of cabinets that had a lot of oil in the bottom of them. And really, if you're only doing this every 5 years, you can end up having something that does fail to operate due to loss of stored energy. Loss of SF6 gas and moisture ingress due to failure of seals, failure of trip and close coils, and sticking or corroded aux contacts. These sticking contacts will result in a lot of coils being burned up, as that is what energizes and de-energizes that trip coil during that event. So we've recently released our breaker monitor. We have quite a few of these in service now around the country. And this is kind of what I feel you should look at when you're looking at doing breaker monitoring. The critical things that need to be seen. We do a waveform capture of the trip coils and main contacts for every event. So anytime a trip coil or a closed coil energizes, it sends our monitor to 128 samples per cycle mode, at which point we will catch a signature sort of fingerprint for that trip or closed coil. And that can also be set for the phase current. So if you have a 2000 amp breaker and you can set a limit on that, and if you exceed that current, then we will also capture that event, and that will help you kind of catch if you have other breakers on your system that are operating slowly. But with this capture, we're able to provide open and close times, arcing times, and latch and main bearing times, which we'll look at in just a second. How much current we had going through the trip circuit, and we also offer trip coil integrity. we do motor monitoring, so starts, current, runtime. But more importantly, we have really expanded this to look at the type of breakers. So with the spring type breaker, we expect a motor run on a close only. That's really the only time we should see that charging motor run. If it does not run, we will send you an alarm. If it runs any other time than that, we will also provide an alarm. However, when you start getting into hydraulics and pneumatics, it's a little more complicated in determining, is that motor run correct? With hydraulic mechanisms, you tend to see motor runs occasionally that are not associated with a breaker operation. This is due to changes in ambient temperature, and as it gets cool, that system will lose pressure, and then you'll hear that pump run to charge it back up. As it begins to warm up during the day, some of that hydraulic fluid will be pumped over into a reservoir, and then at night again we'll have a motor run to pump it up as things cool off. So these runs that aren't associated with operations are common with these breakers. The thing we don't know is what's normal. And the same goes with pneumatic. With your pneumatic systems, you have a leak designed into that, where we want the compressor to run every so often just to keep condensation out of the lines. So what we've done, we've separated motor starts into two groups. We have a operational start and a non-operational start. So either the motor ran when the breaker operated, or it ran at a time when it did not operate. With hydraulic and pneumatic mechanisms, you're able to set a value to that, which will let you get an alarm after excessive runs. So let's say for your breaker, 1 start per day is the normal for your hydraulic or pneumatic mechanism. You could set that value at 1, at which point, if you started getting 2 starts per day, you would get an alarm in. We also provide alarms for hydraulics motor runs, generally on both the open and close. If you don't get those motor runs, we'll provide an alarm on that as well. So it's very comprehensive when we start talking about how the motor's running. And also this is great for leak detection. And really it's the best way to do leak detection. As your motor runs start to increase, that's a good indication that you've developed a leak in your stored energy system. We bring in temperatures for your mechanism, our cabinet temperature and ambient. For SF6, we provide density, moisture, and temperature monitoring. We also provide trending, so we can forecast out to, at your current leak rate, you will have X amount of days until you get to your first alarm point, and this many days until you hit that lockout value of that breaker. This allows you to better schedule your maintenance. And then with heaters, we're doing static and thermostatically controlled. So we're bringing in ambient, so we know if that heater should be running or not running. With thermostatic controlled, that would include your cabinet heaters and your tank heaters. And then, of course, we bring in all the normal operational parameters you would expect from a breaker monitor. So operation count, cumulative I²T values, which is a good recommendation for inspections of contact wear, AC and DC control voltage, and trip coil integrity. So this is the appearance of our waveform capture page. As you can see here, you actually get a pretty good oscillography of the actual event. And then this was a trip, so we have a good trip coil circuit. This was actually on a switchgear type breaker, so it's the reason for the little slower operation and the longer break time that you see. But as I said, these events are triggered on energization of trip coil, energization of closed coils, when phase currents exceed the rated value. And then we also capture auxiliary contacts. We really try to stay away from using auxiliary contacts for any type of timing, except where it's absolutely necessary, as they do stick and develop slack in these mechanisms. So I've seen with a lot of the other breaker monitors and even relays where these times can be very misleading when based off these Oxide contacts due to the AOX might make stick shut. So I've seen events where you'd have a breaker that would open within 30 milliseconds, but the AOX contact would stick, therefore looking like the breaker did not actually open for 800 milliseconds. And you really need to catch those early, because that is going to burn your trip coil up pretty quickly if you're leaving it that energized for every event. Also, we do allow for overlay. So we can store about 1,000 events on board on our breaker monitor. You can select any of these events to overlay another, and that allows us to detect any kind of small change. So if you were looking at this would be the point where we struck the latch, which is what I was talking about, latch and mechanism times. And from this point, this was the time that it took the mechanism to actually roll the contacts open, at which point we see our A contact come open right here in this operation. If we were, say this breaker was to slow down, we could pull up, compare these waveforms, and we may find that this latch time had moved over here to the right on the time scale, at which point we would go in and know that, hey, we have a latch that's sticking on this particular breaker. And I found that when you give very specific things to be looked at, you generally have much better results than you do by simply telling a service crew that, hey, I've got a breaker that's slow. One of the main reasons being you can go operate that breaker 2 or 3 times and generally get a good test out of it. So this was actually a field test that I brought with me, but this again, a little more detail into what I mean when I'm saying latch and main bearings. Again, this first little dip is always going to be our latch, and then this is where that plunger strikes the buffer. But at this point, we should see that our main cam has started rolling the contacts open, at which point our A contact will open, and we should see de-energization of that trip circuit. Again, if I were seeing a sticking latch, I would expect to see this move to the right on the time scale. What you would see more often is this is typically pretty good, but you would see this event dragging out from the main bearing portion, at which point that's a good indication that lubrication degradation on your main bearings of that breaker. So this monitor provides very actionable data to give to your field crews. And also we're catching a first trip operation for every breaker every time. So this actually allows you to stretch out your offline testing greatly, as every time a breaker operates, you actually have a submittable test at that point. So this was the point of setting the setting a capture on your phase current. If you were to, so with any event that happens, as we have this event occur out here, and it could be out here on a line somewhere, everything in that line, everything in series with that particular breaker is going to see that through fault. And let's just say that we have a 3-cycle breaker out here on this line. And I feel like this is where a lot of our transformer damage comes from, and utilities aren't aware it's happening because of the way they're doing their testing. So there's always some type of delay that's going to be set between these breakers. So, you may have 15 cycles between your distribution breaker and your bank breaker. You may have another 15 cycles between your high side breaker and this bank breaker. So if this event occurs here, if breaker operates normally, we clear out in 3 cycles, we cleared this fault. However, if this breaker were to be slow, this fault would have to sit on this breaker for 15 cycles before we would actually see operation of this bank breaker to clear this fault out. In which case, it's a bad thing also, because we also dropped the entire section of bus. But for that entire, so let's say this is opening at 12 cycles. This transformer is seeing that through fault for that entire 12 cycles. It's sitting on the transformer. But if this does open, and this is not, second level of protection is not forced to operate, generally nobody looks at the oscillography off of this. Nobody's aware it's happening. Click through these. So what we end up is with years and years of continued excessive exposure for through faults on this particular transformer, at which point we have that mechanical and thermal effects on the transformer that we spoke about earlier. And with duration, it's interesting because duration tends to lend more to the thermal impact on that transformer. So we'll see a breakdown of the solid insulation, the longer these through faults are held, and eventually the cumulative effects of this will be add up on this transformer to the point that the next little through fault that's nothing will actually fail a transformer. Whereas if we had been aware of this at an earlier point, this could have been addressed. We may have gotten years more of service out of this transformer. So by setting, say we set our monitor here and we've set some kind of trigger on our phase currents, as this fault occurs, if it were to exceed the rated trigger point that we've set for this, we would see that, hey, we did have a fault, even though this breaker did not operate. And I am pointing to the high side breaker. Even though this breaker did not operate, we saw that we did have an event, and it stayed on the operating bus for 12 cycles, as opposed to the 3 or 5 cycles that we would be expecting, at which point you could pull that waveform from the monitor and actually look and see what the duration amplitude of that fault was. So the thermal aging process, how does this affect our transformer in reality? As I said, there's 2 portions. We have the current portion, which is I squared, which is definitely that's our mechanical mover of that core and coil assembly. And then we have duration. Duration attributes largely to the actual thermal degradation we see on that event. And I like to think of this as, we've all seen anything short out. It gets hot a little bit when it first shorts, and it's exponential in how quickly it goes. So it gets really hot really fast. Anytime we're throwing a short into one of these transformers, that's kind of the same kind of process that's happening. And the longer we hold it, the more damage we're doing thermally to that. So what happens when we have this thermal degradation? We see destruction of the solid insulation system, which results in a change in the clamping pressure that's exerted. So when these transformers are new and shipped out, they're clamped to a certain value, and that's taken. When you have that value of clamping force, you've got to consider the amount of mass that you're clamping down on, which includes the solid insulation system. As these through faults occur, we see as these through faults occur, we start to see this solid insulation system degrade, and we actually start losing mass. And so with that loss of mass, we lose clamping force, which greatly reduces our through fault withstand value. Also, we offer on our transformer monitor, we do offer a through fault monitoring. So if you wanted to go and actually see on a specific transformer, the amount of through faults that had occurred, it can be done through our through fault count card. Now, again, this is one of the things that nobody really gives you an exact value of, okay, this is the level of through fault that you can stand on this equipment. We do know that it does affect the life of the equipment. Recommendations on this, and as I mentioned earlier, can't really see it with offline power factor testing. I would probably, my recommendation recently, and after looking at some numbers on this, is maybe take the top 5% of your fleet, that the highest level of through fault exposure, and maybe when you get it offline and run that power factor test, maybe run an SFRA test on that top 5% to see if you had any of these mechanical changes. Again, that's really the best way to indicate this in its earliest stages, and maybe start, you can actually find some where it's like, yes, we have had some large mechanical changes here. Our next through fault, probably going to take this one out, and we can start preparing for that. And that concludes my portion. If anybody has any questions, I'd be happy to take them now.
Okay, thank you very much. Chris, appreciate that. I have a question here. What percent he's asking what percentage of large power transformers have online monitoring installed?
I could not give you an exact percentage. I know there's quite a bit from what I've seen. Now, the interesting portion of that question is what percentage of large power transformers have online monitoring installed that they're actually bringing the information back in, where they actually have comms set up. And that would be what I've run into more than anything. Again, I came from a utility where we probably had been putting a online monitoring on every power transformer that was purchased for the last 7 years, and I would say we maybe had 2 online. So, a monitor that's not talking is something else you're burning up in the fire when you lose a transformer.
That's true. Okay, how would you implement speed testing on existing breakers to avoid the first operation miss?
Again, with our monitor, it's a great way to do it because every time the breaker operates, we're going to capture that. So you get that fingerprint of that waveform, and I've done enough of those to tell you that they should overlay each other pretty perfectly. I typically like to set an alarm point within 10 milliseconds. So if there's a change in operation of that coil of 10 milliseconds, I like to get an alarm at that point because the breaker's starting to slow down. That's not normal behavior for a breaker that's functioning properly. Now, that being said, when you do a lot of this has to be done when you're commissioning the monitoring or commissioning the breaker itself. Most breakers, if you look at, let's just take a 3-cycle breaker for example, generally you're going to see the operation occur somewhere in the low 30 millisecond range, sometimes even high 20 millisecond range. As you know, 3 cycles, we're looking at 51 milliseconds. So it's actually that breaker's a lot faster than the nameplate rating typically. So I would set that alarm. Let's just say we're at 30 milliseconds to make it easy. I would set my alarm point at 40 milliseconds. If I saw that 30 milliseconds at commissioning, that way I could catch that. I would catch that breaker slowing down before it actually reached the point of failure, which is the whole idea of having online monitoring out there anyway, is to catch it before it fails. I mean, that's always been my argument with acetylene, arcing values. I mean, yes, we all know what arcing signature looks like on a transformer, but I'd sure like to know it before it happened rather than being able to analyze it after it happened. So with breakers, we really can see that slowdown over time. If you're not going with the online method, really first trip testing is the way to go at that. It does allow you to test that breaker without operating it, which is timing travel tests are great. I recommend them anytime you're commissioning a breaker, anytime you've done any type of work on that mechanism whatsoever. You definitely need to run those timing and travel tests to get a baseline. But the bad thing about timing and travel solely is it does require operation of the breaker before the test is run, at which point you will lose all that data that was available from that first trip.
Okay, next question. With the solutions you've outlined, are there still offline tests that add value?
Yes, I say absolutely. I think offline DGA test, especially if you're not going multi-gas monitor. My approach when I was an asset manager, I went with key gas monitoring, and then I would use that as indicators that I've had a problem develop between my testing periods. I did offline DGA testing. That was done yearly, and I would do a lot of trending with those values as we talked about. So yeah, I mean, those are great. You still, with transformer power factor, there's really not an effective way to do a power factor on your core and coils while you have a transformer in service. So I would say that's a critical test to keep in your system. So yeah, I mean, there's some offline testing things that definitely offer value. The main problem with offline testing is it's you can only do it so often, as far as getting things out of service. And generally that's about a 5-year period. And with the online monitoring, you're going to see these changes instantly compared to, maybe something occurs within a few days after you did the test, you start having a problem, you're going to lose that piece of equipment when you may have caught it with online monitoring.
Okay, next question. What communications protocol do the online monitors use?
So right now we are doing Modbus. We can do DMP or 61850 with all of our monitors.